Hello, everyone, and welcome to Func Prog Sweden. My name is Magnus, and I'm the host of Func Prog Sweden. Um, Welcome to a new year. This is the first meetup of this year, so welcome to a new year of functional programming. If this is your first meetup with us here at Func Prog Sweden, we are a meetup all about functional programming, both languages, functional programming languages, and also thinking and doing in other things. As an evidence of that, we have one presentation today in JavaScript doing functional programming and exploring functional programming concepts. So let's head over to the agenda for today. First, I will do a short introduction by me, Magnus. Then we'll head over to local first software development with Elixir by James Arthur. And in this talk, introduces ElectricSQL, a sync engine developed in Elixir, and walks through how you can use it with existing web frameworks like Phoenix to develop local first software. Second presentation, Transforming Composition by Kyle Simpson. One of the gateways to get into functional programming is to discover map filter reduce, but that also comes usually, can come sometimes with various forms of, how should I put it? You can get into various forms of problems, issues, and Kyle will explore these and try to take them down and show you how to do it. In the end, we'll do a post-show chat, as always. But first, also thank you Beat for sponsoring the video stream. Thank you very much. And if you want to know more about Beat, just check them out in social media or on otherbeat.com. And the coming schedule for the spring, for the 2025, 18th of February, we're back. Then 18th of March will be also not just online, but also at Kivra. So if you're in Stockholm, make sure to sign up so you can come to Kivra and visit us in real life. And then in April, we haven't set the date, and also we'll be doing one, of course, in April, May. We haven't set dates yet, so be sure to check out the meetup page when we will update the dates and with the presentations that will come. And of course, you want to support Func Prog Sweden, head over and join us at Meetup, and make sure to subscribe to the YouTube channel. And if you want to chat, ask more elaborate questions than you can do in the YouTube chat, head over to Discord and or head over to Meetup, or you can find the invitations link both in Meetup and on the YouTube page to our Discord server. Which brings us over to, if you have any questions, just shoot them in the chat or shoot them on Discord, and I'll take them with the presenters. With that, we are ready to start with our first presentation. Warm welcome, James, to Func Prog Sweden.
Thank you.
Yeah, you're welcome. The stage is yours.
How long have developers been building apps on web service APIs? So writing code like this. I think anyone who's done any kind of web development is used to making this type of fetch request. But then, of course, as we all know, you have to handle all of the failure modes that come with it. So that's like handling the status codes. And if you look at the numbers, like 400 as developers, they're kind of hardwired into our brains, like we know these numbers by heart. There are maybe some fun ones that we might be less familiar with, like 100 continue or use proxy. But basically, we've all written this code here. It's like you make a web request, you're looking at the response. Did it work? Did it go through? Okay, handled the result. If it didn't, what happened? Was it my fault? Was it the server's fault? Should I retry? Do I get the error on the status code, or am I getting it because I stuck a try catch around it and something threw an error? So this is all just very familiar stuff, right? And in a way, this type of fetching methodology, like those status cats are quite cliched, right? They're even super pixelated. They're actually like 600 pixel wide images, and it's an indication that they've been around a while. Like the muscle memory behind this stuff is ingrained, and it's just how you build applications. Well, this talk is about a different way of building software, and it's one where you abstract away this whole domain of fetching and programming across the network, and instead your application code talks to a local embedded data store, and then data syncs in the background. And that way, that paradigm is called local first. So I'm CEO and co-founder of a company called ElectricSQL. Our main product is the Electric Sync engine. So we sync data out of Postgres into wherever you want. So it's mobile apps, web apps, edge workers, working sets, stores, etc. And we also develop a project called PG Lite, which is a lightweight WASM Postgres that you can run in the browser. So you can have Postgres as that local data store inside your local first app. And just briefly, just to be clear, these are composable components, like they work together, but you don't have to use them together. So you can use Electric to sync data from Postgres in the cloud into PG Lite inside the clients, but you can also just use PG Lite on its own. And here's an example of Superbase doing so to build database.build, which is a very cool AI-driven database app builder site that they built on PG Lite. And just as you can use Electric on its own. So you can use Electric to sync into a database, but you can also just sync into something like a JavaScript object or a Redis hash, basically any way you like. And this is an example of Trigger.dev, who are like a background jobs processing platform, and they use it just to sync data into JavaScript in memory for their real-time dashboard. And just to finish the context, we're a startup, but everything is open source, so it's all Apache 2. And you can just get a sense of some of the people behind the company, like we're backed by the founders of Superbase, Cockroach, MotherDuck, Heroku, etc. And also, just to flag it up, by Jose Falim, who, as you know, is the creator of Elixir. And so with this talk, my goal is to first convince you, if you're not already, that local first is a better way of building software. And then I want to show you what we're doing in Elixir at Electric to help you build local first software. And then I'm going to show you how you can use Electric to build local first apps in Elixir and Phoenix today. So let's jump in. Let's talk about local first. One way to think about local first is as the natural evolution, or maybe the natural end game of state transfer. So state transfer, this sort of fundamental concern of how you build software applications, like how do you get the data from the front end to the back end? And if you sort of look at this from a developer experience point of view, it's evolved. Like early on, you didn't have things like Ajax, and then things consolidated on REST, and then GraphQL started this process of abstracting away state transfer out of the application domain. And local first is kind of the natural end game for that. It fully abstracts state transfer out of the application code, so the application code just talks to the local embedded database. And from a UX point of view, if you really boil it down, this is my highly sophisticated diagram of all web apps. Start with the top left. The user clicks on a button, sends a request to the server talks to the database, sends a response back, the user sees the result. And the problem with this is that you have the network on the interaction path. And so as the application developer, you don't control the network. So your availability, the quality of your application's user experience is determined by factors out of your control. And you spend a whole bunch of time coding around the dictates and challenges of this client-server bridge. So authorization, serialization, error handling, status codes, etc. Whereas in comparison with local first, you basically make one small change to the architecture, and that's to move the data store into the front end. And with this, the application code can talk to the local data store first. That's why it's local first. And then the data syncs in the background. And it takes the network off the interaction path. So you don't need to spend all your time coding across this client-server bridge and dealing with all of the problems. And as a result, with your user experience, everything's instant. It's super snappy. You get multi-user collaboration built in through this background sync, and you own your own availability. The apps are super reliable, so they work when they're offline. They work through patchy network connectivity. They're not reliant on the server being online or compatible to keep functioning. And so that's a quick overview of why I'm arguing that local first is a better way of building software. And so let's move on to what we're doing in Elixir at Electric to help you build local first software. If we come back to this simplified diagram, local first is based on sync. Like that's the horizontal line in the middle between the DB and the server in this diagram. And actually there's two parts to it. You have the read path sync, which is to get the data from the server into the local app. And then you have the write path sync, where you're syncing local changes off the device, usually back into a server or database, but potentially like peer-to-peer or a bunch of different topologies. And the write path has a bunch of very well-known complexities, especially to people who are familiar with distributed systems. You have concurrency challenges, conflicts, difficulties maintaining integrity and user intent. And actually, these are quite application dependent. And so I'm going to come back to these in the next section. And one of the examples I want to show about how you can develop local first with Elixir now is to walk through a number of write path sync patterns. But before we get to, in a way, those hard problems, there is a more fundamental problem that you need to solve, and that's the stale data problem. So the whole point of a local first app is that you have the data locally. But of course, if you have the data locally, then you need a way of keeping that data up to date. So if you take this fetch example we started with and you stick it in a listing page, so you load the data when you render that page, what happens when you navigate away to another page and then come back to the first one? Is the data still up to date? Do you need to refetch it? Do you block with a loading spinner whilst you're refetching? Or do you show what you have and then update it once the new request comes in, causing your listings to flicker and move around? Do you do what Blue Sky does here, and you have a little new indicator when you're notified that there's changes, and you make the user click and they refetch and they scroll and then render up? And without getting too distracted here by the dog whistle of our new fascist overlords, the point is that this is exactly the type of imperative network-aware coding that we're trying to move away from. So instead of you as a developer taking care of keeping the data up to date, you want a sync engine to do it for you. And that, of course, is what Electric is. So with Electric, instead of fetching data like this and then handling all these failure scenarios, you tweak your code to sync data like this, and then the system just takes care of it for you. And if you look at an example application, this is a quick snapshot of a linear clone that we built with Electric. It has 100,000 GitHub issues synced into it, with I think 200,000 comments. They're synced into a local PG-like database. You can filter the app, navigate, all the data's just there. So everything's local, instant. And I think I'm just going to like navigate to a screen, add a new item to the database, you go back to the listings, the item's just there. And of course, it would just be there whether you added it or whether somebody else added it. So the system is just taking care of keeping everything automatically up to date. So as a developer, and from the viewpoint of your application code, you can trust that that local data is up to date. And so how do we do that? Well, technically, Electric is a web service itself. It runs in front of Postgres, and it connects, as most applications do, via a database URL using a standard database user. And it connects using a kind of normal interactive query access, and it also establishes a subscription to a logical replication publication. And then it provides an HTTP API that clients consume over long polling. And that may be surprising. You may wonder, if this is a real-time sync system, why does it not use WebSockets or another protocol? And actually, it's because by using standard HTTP with long polling, we can integrate into existing application stacks much better, and also tooling like middleware and CDN infrastructure. So it actually turns out to be much more scalable, reliable, and better performance to use more old-fashioned long polling than to use kind of newer stateful sync protocols. As I say, it's just an Elixir app, or it's an Elixir application. The source is all on GitHub. I can share links later, but it's on the ElectricSQL GitHub. And basically, it does this scalable fan out of data from Postgres to clients. So if you look at this diagram, the sort of solid blocks from Postgres to client on the right are what Electric is doing, consumes the logical replication feed, and it fans it out into what we call shape logs. And then clients can subscribe to those shapes. And so we do sync, but we do it with partial replication. So you're not necessarily replicating all the data. You can choose a subset of the data that you want to sync into the client. And we do that through this primitive called a shape, where the idea behind a shape is that it's very similar to, say, an ecto query with an association graph. So you can pull in like a tree or a DAG of data, and that's just like a subset of the data from the database. And a shape might be like a project with all of the contents of that project. At the moment, actually, the implementation of shapes that we have is still relatively limited. So it's single tables with where clauses, but we're working towards providing a more expressive shape interface through Electric. The kind of idea is that you can do a richer definition of partial replication. And then in order to deliver that, we leverage the Beam, the Erlang VM, for resilience, concurrency, and we basically do a lot of GenStage-based data processing. I don't know how readable this slide is, but I was digging into the Electric code to kind of what's the best way of illustrating that. And this is a module doc string kind of just discussing kind of some of the supervisor tree infrastructure that we sort of spin up through the kind of pipeline to process this sort of data stream and fan out. So you can kind of get a sense of the sort of type of wiring within the application. It's a bunch of kind of OTP, GenStage stuff, and that's helpful both to kind of harness concurrency, and sort of make the right trade-offs in terms of the performance engineering of the system. And if you look at some benchmarks, for example, this is showing the sync time for a single shape to go to a client based upon the number of rows in the shape, and it goes from like 1 row to 1 million rows. And as you can see, the sync time scales linearly, and important on the graph on the bottom, the memory is relatively flat. It is essentially flat. So like what we've done is try to engineer the system so you don't get this thing where your sync system explodes in memory or any other compute resource when you start to get higher throughput. And instead, we can just handle these things with sort of known flat or linear resource use characteristics. This is another graph here, which just demonstrates with write fan out. So the previous one was about sort of serving data out to clients, and another performance thing is how quickly can we write the data out of Postgres into shape logs, and that determines you have these change messages coming through the logical replication stream. And then the question is like, how many shape logs do you need to write those change messages out to? And what's the expense of kind of doing the matching? And so this demonstrates, again, that it's relatively linear in terms of the number of concurrent shapes that you're writing to. And there's some trade-offs here that I'm happy to go into depth on in Q&A if it's useful. But basically, what I wanted to get across is that we've engineered this core Elixir service to be sort of zero surprises in the way that it scales and uses the compute resources. And then that's the kind of core server itself. But because, as I mentioned, we serve over an HTTP API, we actually scale out the data delivery to clients through existing CDN infrastructure. So think of things like Cloudflare and Fastly. So for this kind of read path sync, there's two aspects of it. You have the initial sync, which is when a client wants to request the data that it doesn't have. It's like subscribing to a new shape, so it has to get all the existing data. And for that, what we do is we query Postgres, we write into a shape log, and then we serve that shape log out, and it's essentially batched arrays of JSON documents, and that allows it to be just served as basically static documents, which can be served through a CDN. And so if you have multiple clients, if you have concurrent clients that are accessing the same data, then they can just be served through the CDN. And so that takes that query workload off not only Electric, but also the source Postgres. And in practice, if you deploy Electric as a system to get data into wherever you're choosing to sync it into, it often radically reduces the query workload on the source database. And then the other aspect is if you have a client that has got a live subscription and it's monitoring for real-time changes, because we use HTTP with long polling, we can leverage a capability of existing CDNs called request collapsing, which is that if a CDN or a reverse proxy that supports this gets multiple requests to the same URL at the same time, it only needs to send one request onto the origin server. So you can have 100,000 concurrent connections coming in at the CDN layer, and only one comes through to Electric. And so that's the way that like the core system is engineered to be scalable and reliable, but actually the data delivery just leverages this existing CDN infrastructure, which is obviously highly mature and tested at scale. And this here is a summary of the sort of benchmarks that we run with a CDN in place that demonstrates scaling out from 1 or 100,000 to 1 million concurrent clients. I think the overall workload was delivering around 80 gigabytes per second. And as you can see, the latency is flat from like the minimum to the maximum number of clients, and so is the memory use of the system. So this demonstrates scaling out to 1 million concurrent clients for a high throughput real-time data workload. And basically Electric is perfectly fine with the compute resource, and the source Postgres doesn't even notice it. So it's a way of running these very large-scale real-time workloads on top of just an existing standard database infrastructure without adding additional resource load or any sort of concerns around exploding compute use for that existing infrastructure. So I hope that gives you a bit of a sense of what Electric is and how we've been trying to approach engineering it and why we're using the Beam and Elixir. So now I'd like to go to the third part, which is to go into some actual code to show you how you can use this. So I'm just going to come out of presentation and jump over. And so I'll just set a little bit of context by looking at the Electric site. So as I mentioned, I'm just going to kill Zoom. I'm not sure if you can see it, but I can. Anyway, so as I mentioned, we send data out through this HTTP API. You can see here, for instance, that this was literally just a curl request in terms of how you use the system. Now, if you think about doing this read path sync, there's two other aspects that you then would need. One is authorizing access to the data, and then the other one is how you do the write path sync. And so those are two of the examples that I want to show you, but also just in terms of using our core API. So this is the kind of underlying HTTP API, but of course that's wrapped up into client libraries. And so like this, for example, is our core TypeScript client library. You establish a shape stream, you materialize it into a shape, and then you can just basically get notified when it changes or just access the materialized value. And that, for example, is what underpins the use shape hook that I showed you previously in terms of changing the code from fetching to sync. And then, but we also have a first-class Elixir client. So again, using Elixir, here we can establish just an electric client subscription to a shape, and you just consume this stream and you can materialize that stream into a data structure. So Elixir for us is a first-class kind of client platform for Electric Sync. And then for a more comprehensive integration, we have a Electric Phoenix package where it does two things. One is that it integrates in to the Phoenix Streams capability of Phoenix Live View. So what this does is allow you to, if you're taking a collection and passing that to the front end of the live view, rather than just having a static collection, you can use this electric stream function instead, and then electric just keeps the function live for you. And the Phoenix Streams mechanism, which makes it efficient to update collections over the wire to the front end without having to hold the whole collection in memory on the server side, we actually tap into almost one-for-one in the sort of types of messages that come over our replication stream and that you would serve over the Phoenix Streams API. And so what this does is it allows you to basically make live view applications which bind to shapes out of your Postgres database and then are just real-time out of the box, which is a very cool mechanism of building real-time software without having to write any JavaScript whatsoever. And I'll jump in and show you an example of this. But that's cool, but it's not kind of fully local first in the same sense. And so what we've also done is, I don't know, you may be aware, but Jose Valim did a Elixir keynote a while back introducing his vision of a library called Phoenix Sync. And we've worked with him to effectively implement Phoenix Sync using Electric. And so what this does is it allows you to integrate Electric into a Phoenix application and serve shapes based on Ecto queries. Again, I will just dive into an example that shows you that. But basically, this is a way of exposing sync through a Phoenix application. Now, those two key aspects of development that I mentioned before, so auth and write. Now, with authorization, when you use a sync engine, most people would think that you would have to use some kind of rule system to authorize access to the data, because in a sense, you sort of lose the flexibility of that end layer. But with Electric, because we sync over HTTP, you can still route the stream through a proxy. And so you can use a proxy as an authorizing proxy to control access to the data. So when you are saying, I would like to sync this shape into this client, or if a client is requesting that shape, you can say, okay, what are your credentials? Which shape are you asking for? And you authorize access to it just the same way you would authorize access to any other web resource. And of course, you can use any web framework for that, including any Elixir framework, but it works very well with like Plug. And if you have an existing application that's been built using Phoenix, where you may have, say, a Plug-based authorization middleware, it's very easy to repurpose those to use them with Electric, as opposed to having to work out how to codify them into something like RLS or Firebase rules or something. So that's a key aspect of in practice, in reality, when you're deploying this stuff, you need authorization, and Electric is designed to be able to be used with the authorization primitives of your existing web framework, including Phoenix. And then with write, as I mentioned previously, there's a fair bit of complexity and concerns around, say, concurrency and rollbacks that are kind of quite well understood around this type of system. Electric doesn't prescribe a solution to write, and instead we document here a number of patterns where you can implement some different approaches to the write path of your application. Now, I'll walk through an example of these patterns, but the key thing is that they all work by essentially posting data to your API so that you can use your existing API to handle those, write them to the database, and do any authorization on the write path that you want. So again, Electric is designed to work alongside an existing like back-end web framework, which can be anything, but works very well with Phoenix. And again, you could be reusing similar authorization middleware for kind of read path and write path if you wanted to, and just repurposing or reusing the existing layer that you use to handle writes in your application. And in fact, with some of these patterns, you can just use exactly the way that you would do writes for, say, an API-based application, and then use Electric alongside on the read path and still get a fully local first application. So I'm just going to now dive into some code. So this is our repo. We have an examples folder. You've got a bunch of examples in here. The first one I wanted to show is just the our Phoenix Live View example, which uses that Phoenix Streams integration. So this is a Phoenix application. If I go in to just show you the code, it's a to-do list app. We have like this is a live, and here, for example, we're just showing you that when the live view mounts, we use Electric Stream to send the result. So this is actually basically sending an ecto query by just saying query all of these to-dos, and that gets streamed through us the to-dos collection into the client. And then in here, we handle writes inside the live view just the way you would do it with a normal live view, which is just we're handling events. And so like here, deleting or toggling completing. I think this is the actual form component for adding a to-do, and you can see here it's just like there's just standard code for adding a to-do. And so basically if I fire this up, and then just jump into it, here it is, and it's just a standard to-do list application built with live view. But the key thing, of course, is that it is just naturally real time. So one of the things I can do here is if I just pull up another web browser, you can do the kind of standard real time thing, and it just gets the same data. And if you write in one, you write in the other. And you can just sort of interact with them as you wish, and all of the data syncs, of course. Now, another nice thing of the Electric system, of course, is it's all just Postgres. So everything just syncs automatically out of Postgres. So you can write through an application like this, but you can just also write directly in Postgres. So if I just open up a PSQL client to the Postgres, and if I wanted to, for instance, set all of these to-dos to, I just wanted to get it so you could see them at the same time. Let me just move this up. There we go. You can just update the database and everything just immediately syncs through. So it is a very nice way where there is basically zero additional wiring to your application to make it real time. And there is no silo in your data model. It is just Postgres, and you can have any application writing to Postgres and everything just syncs. So this is a pretty powerful and productive paradigm for building real-time applications in Elixir. But if we were to jump through to a more local first example. So what I'm going to do is I'm going to run an application which basically runs all of the different write patterns that I was just showing before. Now, before I do, what I just want to show, I want to show another one, an example around auth, where one of the patterns that we have for auth is to use your Phoenix application as a proxy. And here we have a Phoenix application in this gatekeeper auth example that implements that. If I just jump into it just to show you, it's basically you have a gatekeeper endpoint which uses this Electric Phoenix library to expose streaming a shape through your Phoenix application. And then we just have a proxy endpoint here. So sorry, this gatekeeper application generates authorization tokens, and then this proxy endpoint actually streams the shape through. And this is just set up as a standard Phoenix router. And here there's two pipelines, and they basically just use plugs to do the authorization logic. So the pattern, I can show you a little diagram of it here. somewhere. Yeah, here. So if you can see this okay. So basically the pattern with this app is that the client wants to stream a shape, but you are protecting access to the API through which they can stream the shape using this gatekeeper endpoint. So you would post user credentials to the gatekeeper endpoint saying, hey, this is me and I'd like to stream this shape. The gatekeeper endpoint then returns a JWT, which is actually a shape scoped authorization token. That is then added as a header to the request where you're wanting to proxy the shape stream. If that's authorized, then you make the request to Electric and then you stream the data back through the proxy. So that's the kind of flow. Now, the key thing is that if you actually look at this, we have a plug here where we do a little bit of Electric specific stuff to go with the Electric API. You define your shape in your request parameters. And what we do here is we basically just go assign the shape to the plug context, to the plug assigns based upon your request parameters. And then when it comes to the gatekeeper endpoint, we pipe through a gatekeeper pipeline that assigns the shape. And then we basically have two just fake things to go authenticate the user and authorize the shape access. Authenticate the user is just dummy. You just assign dummy to current user because this is an example. And then when we authorize the shape access, basically we're just saying if it's the dummy user, it's authorized. But this is where you could do any kind of arbitrary logic to go, is this user allowed to access this resource? Because you have the current user available and this is just standard middleware code. And then when it comes to the proxy, we're then able to authorize the token that's returned from here, where we have a pipeline that says, okay, again, get the shape from the request parameters and just verify that the token is authorized to access the shape. And that's kind of what this verify token does. It goes just authorize it. And we have this authorizer class where it basically generates out a token, a shape scope token, and it authorizes that token. So I know I'm going through this quite quickly and there's quite a lot of specifics here, but I just wanted to kind of show what I hope looks to you like very standard Phoenix code. These are standard endpoints. These are standard plugs. This is how you can achieve authorization. And in addition, if you imagine that you wanted to handle writes in the same application, it would be very, very easy for you to just expose APIs alongside this within your application, just as you normally would, right? Like here's the actual proxy controller implementation, but you could easily have a write controller and you'd just be able to use the same middleware to authorize writes. So I just wanted to jump into that code to give you another context of kind of how to do that sort of authorization pattern. Now, if we move on to writes, let me just basically fire it up so you can actually see something. So in the write patterns here, I'm just going to basically run the application. And here we go. So what we have is we have these four apps all just sort of embedded within the same app, or they're just React components, all part of the same React app. And they all implement the same to-do list application, but they do so using a sort of progressively more complex write pattern. And so in all of these applications, it's using Electric to sync. So like we saw before, you add to one, it syncs into the others. This is all going through Postgres, obviously. Now, what you then get is that the first pattern of going, okay, Electric does read path sync, but how do I do the write path sync? Is just to use a normal API to do writes. And that's what this online writes example shows. So it just basically posts data to an API to write the data. So if we look at the source code here, this is a React application. This is our function basically for that app. We have our use shape hook, which is syncing data in from Electric. That's where the data comes from. And then here we have three functions, which are like create to do, update to do, and they all just basically like just do a standard CRUD operation by posting it to an API. So create to do, update to do, delete to do. And then down here, we just have the kind of interface in React for like render the to-do list. And if you click it, it toggles the to-do, and if you delete, it deletes it, and there's a form here to add it. So that's what we're just seeing in the page here. And you can imagine the API that's handling that just being a Phoenix API. Now, The downside of just doing that, of course, is that the application requires the API to be online. So if we look at how it behaves if we turn the network off, so I can go here and set this to offline. Now, we've sort of done the best we can because we have a resilient fetch client. So basically, we can see in the network tab that that request has failed, but it is backing off. It's both trying to sync the data from the client, sync the data on the read path, and trying to make that right. And so if I turn it back on, the kind of best we can do with this simple online example is that once the back off algorithm sort of catches up, the write goes through, and then when it goes through, it'll sync back to everyone else. So that's an example where you do still get some offline resiliency, even just without handling any kind of optimistic state. But a slightly more realistic example, which doesn't require too much boilerplate, is like if we look over here, we have this optimistic state pattern. And so here again, I can just like sync an item. Now, if we look at the code for the optimistic state example, it's very, very similar. There's two differences. The first one is that we import the standard use optimistic hook, which is available in the latest React release. And we import something to be able to monitor the replication stream to kind of see when our writes are synced through. And so then what we do in here is it's basically a component again, and we use the use shape hook just to sync data in. All of this is very similar. And then the difference is that we have this built-in use optimistic hook, which provides you this function so that when you're doing a write, you can register some optimistic state. And then all that this is doing is basically merging that optimistic state into the to-do list that's being rendered. So if it's an insert, you add it to the list. If it's an update, you patch the properties. And if it's a delete, you remove it from the list. And this is very standard stuff, right? There's now built into React. It's a kind of blessed pattern. It's sort of very common. It's maintained. And then these create, update, delete functions are basically exactly the same as before, except that rather than just doing this here to post the data to the back end, we do it inside a transition. We first add the optimistic state, then we make a post request to the server, and we also monitor the replication stream for that write coming through. And then what this allows us to do is basically display the write to the user instantly so that the application functions for users offline while still basically waiting for the request to go through. And so if we come back here to this example and I turn this off, then it does what you expect, which is that the state is kind of here, shown to you automatically. This little spinner is showing you that sort of transition still active. And then if I turn it on, then it'll sync. It basically syncs through, and it removes the optimistic state, and it syncs through to the other applications. So this is very, very little boilerplate on top of a kind of basic pattern for doing an API-based application, but you already have an offline capable, essentially sort of partly local first application. Now, the next pattern, there's two more patterns here, which I'll go through, and they are maybe a little bit more powerful. The shared persistent approach extends this idea of optimistic state, but the weakness of this use optimistic approach is the optimistic state is just within the component. So it's not persisted, and it's also not shared with other components. So this shared persistent example, we do again, just extend things a little bit where there's a little library here called Valtio, which is just like a reactive local store. So that's a way of having a very simple in-memory key value store that you can also just subscribe to changes from. And we still import the React transition, and we still have these matching stream utilities. And so what we do is we just say, right, the optimistic state is a instance of this Valtio store, and we also persist it to local storage. So basically, when the application loads, we hydrate it out of local storage, and when you write stuff, you write it to local storage. So that's the kind of additional code to basically make this client-side store for sharing optimistic state across components. And then because this is a slightly more realistic pattern, we've also made our matching logic a bit cleverer so that instead of just matching on the row ID, we generate a unique ID for each write. And that allows us to do slightly more sophisticated merge logic because we can apply the local optimistic state on top of other concurrent operations from other users, and we only remove it when our write syncs through the replication stream. So these patterns are just showing a sort of slight increment in the complexity of the merge logic with these optimistic writes. So basically we have a function here of like adding a local write to the optimistic state. We have a function for matching a write, and then we have a function for making a request. And then basically everything's exactly the same. So it's a transition, it's the use shape. We have a very, very similar function here for just applying the optimistic state. It uses this Valtio store, but otherwise this sort of merge logic is exactly as we saw before. And then these functions are almost exactly the same. So it's just create to do, and then we start a transition and we apply the local state and we make the API request and we match the stream, but we match it in a slightly cleverer way. So again, it's very little additional code on the example that we were just seeing, but what we get with this example is really quite a comprehensive local first application, because you can have multiple components that are all sharing this client-side state. The pattern is that you sync into the data that you sync is immutable from the server, and then you have this mutable local optimistic state that's merged on top of it, that's removed once your writes have been confirmed as syncing through the replication stream. And as you'd expect, the behavior here is like the same. It's obviously you can just write and it displays it instantly, and you flick the thing on again and it kind of the write goes through and then it syncs through to the other applications. And then just the last thing that I wanted to show is then this through the DB sync pattern. So, I mean, typically syncing through a local embedded database is regarded as quite a complex challenge. And what we've tried to do with this pattern is show that actually it can be relatively simple. And in this case, what we do is we make writes to a local embedded database, and then we detect those, and then we post change sets to the server. So it's not quite the same as just doing exactly the same as you might do with like a REST API handling a write. You would have a slightly different write endpoint, but actually it's still something that would be very straightforward for a backend Phoenix app to handle. So a lot of the complexity in this example is based on a local embedded PG Lite instance in the web page there, and this is the schema for the local Postgres database. And the trick is that where you have a table, you actually have two tables. One is where you sync the state from the server and you treat that state as immutable, and then you have basically a shadow table for local optimistic state. And then you can do some trickery in your database schema to combine those into a view, so you can then query it as just a unified table. And you can also use, instead of triggers, I'll just jump down to the, so here, this is an instead of trigger that basically says when you do a write operation, it intercepts it, it writes it to the local mutable store, and it also writes it to a change log that you can then sync. So there's a bit of scheme here that's probably a little bit too much to go through in more detail, but it's about 350 lines of SQL, and it's very, very generatable. So like this is handwritten SQL, just demonstrating doing it by hand, but it would be very easy to make a generator for this for when you are creating a table. It sort of emits this kind of boilerplate. And basically it also, when you stream in a new item to the synced tables, it basically looks for the optimistic state, looks for this matching on this write ID, and removes the local optimistic state. So the optimistic state is removed in almost exactly the same way as the last example with the shared persistent pattern. And with that complexity there, if you actually look at the application code, it is extremely simple. So we have a little bit of PG Lite boilerplate to instantiate PG Lite, but then if you look at, and that's what this wrapper basically does, it just instantiates the local embedded database. and it also instantiates a sync utility, which I'll just go through next. But then when you come down to the actual component that we were looking at, as per the other examples, you get a handle on the local database and you use a live query to just get the to-dos, and then that's it. You have these, you can just have functions where you just write directly to the local embedded database. There's no need for any awareness of optimistic state. There's no sense that that operation could fail for some sort of network reasons. You're not coding across the network. This is literally a embedded local database in your application. And so it's very, very simple to just use SQL to insert, update, delete. And that's that, basically. And if you look at the behavior again with the application, it's just exactly what you expect, right? Everything's just instant and it syncs through, and obviously it's supported offline. In this case, we don't have the same spinner because it's just not needed, because actually the operations are accepted into the local embedded database. And so, you know, you turn it back on and everything syncs when the network just comes back on. So, I mean, this is an example of a very proper kind of full local first application using an embedded database where authorization and rights could be handled through a Phoenix application, and the read path sync can be an Electric instance embedded into the Phoenix application. And again, there's just one little extra bit, which is that we have a little utility here, which just monitors a change feed table and posts them to an endpoint. So there's just a little bit of sort of control flow logic to monitor this table. And then basically we batch up changes and send them through as an array of transactions to the back end. But as I say, it's a relatively, you're then just basically going, okay, I've got a batch of transactions. What do they contain? It's a write to this object. And so if you want to go, does that user have the rights to write to this object? You could just do that on an operation by operation basis. And if you reject the rights, then the local schema has got the stuff built in to be able to go, okay, that right was rejected, so we can roll back the local optimistic state, and the application is always in a consistent state. There we go. So I hope that was interesting. Very happy to answer any questions on these examples. Maybe just to note again, if it's interesting, so electric-sql.com, we have a Discord channel which you can join. There's about 2,000 people in there, and this is our GitHub here. We're GitHub electric-sql, and you've got both the Electric repo and PG-Lite, and PG-Lite also has its own website and documentation here. And so that was that, and I hope that if I come back to it, I've convinced you that local first is a better way of building software applications. I hope you understand how the Electric Sync engine fits in to being a component that can help you compose a stack to build local first applications. And I hope it was interesting to see some of the primitives that we built to use that in Elixir, both the Elixir client and this electric.phoenix library, which is up on Hex, and you can just sort of follow the documentation for. Thank you.
Thank you very much, James. Thank you for a very nice presentation. People are saying like they like it. Thank you very much, James. Cool. First question. Where did you get the idea to build like local first? What was like, was this something I need it, I want it?
Yeah, I mean, it's interesting really is that when we started the company, we were building on research into distributed database systems. So like not me, but a number of my colleagues and our advisors had invented a lot of stuff to be able to build systems with more consistency and integrity on top of active-active replication and the sort of AP side of the CAP theorem. So our first idea was like, let's build CockroachDB, but for the AP side of the CAP theorem. So that's sort of where we started. And actually we were building on a Erlang-based system called AntidoteDB, which was a prototype that the academics that we were working with had built, or slightly more than a prototype. It was actually really quite well built and maintained system. But then you sort of dive into like, okay, but how do people want to use this, and which problems are we solving for people? And we sort of rethought of using the same algorithms to do a replication layer behind existing open source databases. And so you had this idea of like active-active Postgres and Postgres to SQLite. And then we were digging into use cases for that. And that's really where we realized that there's quite a lot of people in this emerging local first software space who are trying to build on these types of patterns. And we sort of, again, reconceived what we were doing as a sync layer over this sort of last mile state transfer between the client and server kind of setup rather than like a sort of distributed multi-region database. So that's slightly how we stumbled into local first. And we then spent like a while trying to build a more integrated end-to-end local first software stack. But then last summer, we sort of got to the point where we were getting a bit bogged down in the complexity of that, and it was just a bit too much to deliver on what we were trying to do. And so we've simplified what we're doing back down to this read path sync and tried to make a much more composable system that we could actually productize and people could build applications on. So it's been quite a sort of journey of, in a way, sort of stumbling into the area, understanding which problems were solved and which ones weren't, and sort of trying to build software that's useful for people.
Interesting, thank you. You mentioned at some point, like you made a choice of Elixir or building on the beam. Did you ever consider anything else, or was it like, no, we're building it on the beam and that's it?
Yeah, I think the sort of truth is that certainly for me, as an Elixir developer coming into the project in the kind of early days, it was such an obvious fit. And also when we were first building on AntidoteDB, which was based on the beam in Erlang, like we sort of started off with ideas of going, well, how would you integrate AntidoteDB into a library like Ecto? We actually like built out a library called Vax, which was kind of doing just that. So our earlier ideas were that we wanted to sort of take the underlying research stuff and make it accessible to Elixir developers. Now we're much more of a sort of generalist platform where you can use this from any language, and a lot of people are using it from JavaScript because that's how more client systems are kind of built. But in terms of the actual sync engine itself, it's such a fantastic fit. I mean, we really do lean very heavily on GenStage, OTP, supervision trees, concurrency. That probably in the beginning it was just kind of such an obvious choice, didn't really overthink it, but it's not something that we've ever kind of thought about changing just because it's such a fantastic match.
Thanks. Final question. Is there any competition or like alternatives or other like solutions to this?
Yeah, I mean, there's some very cool projects, and there's a lot of really cool projects in this local first space that are well worth checking out. There's like a lo-fi Discord, which is really good for kind of like picking up on a range of projects. They have a website as well, which was called Local First Web, or kind of lo-fi software. And there's a variety of projects from different angles. Like there's cool projects I could list off would include things like Zero. So there's a project called Zero Sync, which is by the developers of Replicache. And that's a fantastic also sort of Postgres based sync system, which is doing quite a lot of clever stuff to sort of manage how data is synced into the local client. It's a bit more end to end integrated and sort of smarter about how it manages sync for you. There's a great project called Jazz, which is a sort of batteries included local first stack and sync system. There's one called InstantDB, which is a little bit more sort of graph orientated and sort of viewed as like a successor to Firebase. But they've done some very clever differential data flow based kind of sync stuff for sort of partial replication of a graph model. And it's still persisted in Postgres, although it doesn't work with the sort of existing Postgres data model out of the box. You sort of adapt it to their data model. I mean, and there's a lot of others. PowerSync is also another system which does this type of local first sync on an existing Postgres model. And that's quite mature and has been had a lot of people using it for a long time. So there's a lot of these really quite cool projects in this space because I think a lot of people have seen the patterns. Some of the underlying challenges have been kind of solved. And it's sort of clear that as an application developer, like for example, like Figma and Linear famously spent millions of dollars developing their sync technology because they wanted it to be a differentiator of their products. And it's really worked because they've been able to make really high quality products. But when you look at it, actually it shouldn't be that every application is building its sync engine. It should be the sort of type of thing that can be solved by a framework or a library for you.
True. Maybe it will be commoditized in the end, meaning that it will converge to a separate, I don't know.
Well, Martin Kleppmann, for instance, So there was a local first manifesto paper that was written by Ink and Switch, which is a research lab that has sort of pioneered a lot of the thinking around this, and Martin Kleppmann is part of that. And one of his visions for local first is a standardized sync protocol. And so it's quite interesting to sort of think, yes, a lot of the ambitions behind local first are around, there's these sort of there's considerations around like just making faster software and sort of better UX and better DX, but you also have aspects of data ownership, and you don't want to have to kind of give your data to the cloud and have that exploited. And so with that sort of more ethical mindset on it as a software movement, you also want to think, okay, how do you have, say, data interoperability? And so that's like, there's a bunch of thinking that Martin's developing around that kind of like, what would a shared sync protocol look like for local first software, that I think is going to be really influential.
Again, thank you very much, James, for today. Thank you very much. People are giving you big thanks in the chat. So thank you very much
Awesome.
again, James. Yep.
Thank you all. Yeah, great to be here. Cheers.
Yeah, you're welcome. You're welcome. Thank you. Now we will head over to our second presentation of the day with Kyle. Welcome, Kyle, to Func Prog Sweden.
All right, let me get my slide shared here real quick. Give me one
sure.
sec.
So Kyle will present how we can do FP in JavaScript.
Sounds rather heretical, I know.
It does.
Okay. Uh-oh. We've got to swap those two.
Nice. The stage is yours, Kyle. It's yours.
All right. Thanks, everyone. Appreciate you being here. And I just have to give a shout out to the first speaker, James. I am also very interested and active in the local first space. I've heard James speak a number of times at those meetups and seen him participate in a lot of the discords. It's a fantastic community, and he's definitely one of the leading voices in that space. So I encourage everyone, if you've been interested in local first, you have yet another speaker who's echoing that we really do believe this is the future of the web and of software development. And I work for another company in that space. I just recently started a company called Source, and we also make database and synchronization things. We have some different takes than ElectricSQL, but there's a lot of fantastic options in that space. So with that out of the way, I'm not going to talk about local first at all. We're going to talk about some functional programming concepts, specifically around the composition of data. This is something that has come up a whole bunch of times. I've been asked this over and over again, and I've had different code samples and gists that I like drop for people. I've written blog posts, and I decided I really just want to have like one canonical place where I give this talk so that I can refer people back, because this comes up a lot, and I would imagine many of you have probably run into issues like this. And I want to say that even though I'm going to use JavaScript, there are bits and pieces of what I'm going to describe today that are somewhat special or somewhat related to JavaScript, but a lot of these concepts are really broadly applicable to a lot of languages. So the goal is to understand those concepts, be able to apply them in JavaScript if you're working in JavaScript, but hopefully at least have the right terminologies, the right libraries, the right kinds of concepts to look for if you happen to work in other stacks. So with that said, let's dive in. I'm going to set us up with a running example. We have one single running example that I'll go through in all the slides, and we'll approach it in various different ways. So here's some setup code. A little small. I'm going to give you a moment to kind of grok what you're seeing here, but this is just some real basic setup stuff. I'll direct your attention to the bottom, the get mock data. I'm not doing any asynchronous API calls or anything like that. So we're going to literally just for these examples look at synchronous data that's already there, but we're going to treat it as if it could have come from somewhere else. And by the end, we'll actually be able to have abstracted that away, that it wouldn't matter if that was some asynchronous API call that we've gotten to. But to keep the code simple and straightforward, here's what we're going to work with. So the lookup movie it's a synchronous function that just grabs stuff out of that object that's in the mock data variable. And so that's the context that it's always going to be referring back to this list. I just pulled out a couple of, globally known movies from the last 100 or so years and kind of put them into a list. So this is our basic example we'll go through. Let me direct your attention to the three functions in the middle: valid movie, recent movie, and format movie. We're going to be using those in various combinations along with the lookup movie function. So that will kind of define our flow of data. Note that valid movie and recent movie are what we call predicates in functional programming. You probably know that term. It just means they return Boolean. So they're used to make decisions. We pass in a piece of data, we make some decision about it, and we say true or false. Lookup movie and format movie are different. They're not predicates, they're mappers. Their job is to transform data. So they take in something like movie data and return something else. And so, for example, the lookup movie takes in a movie ID and returns an object, whether it had to go through some steps like an API call, it just returns it's an object. So that was one transformation. And then we transform from a movie data entry into, in this case, a string that just prints out the movie title and then the year it was released in parentheses. So we've got predicates and mappers. Those are the kinds of items that we end up in our application code kind of working with. That's our setup. And then we will start by kind of as our baseline, implementing a very simple data flow that will do so in the imperative coding style. In the context of the code and of programming, this term imperative, it gets thrown around a lot, but it means code's primary objective is to express how to do something. The reader has to mentally execute the code and then infer its purpose, the what or the why, after doing so. They can also optionally pick up on context clues such as the identifier names, the code comments, etc. And that style is contrasted with declarative, which is code that focuses more on the what and the why and allows something lower in the abstraction stack to handle the how. So the goal of most programmers is to try to elevate to a more declarative plane of abstraction. There are a variety of ways that we do that, and by a variety, I mean nearly infinite. And it should be seen not as a binary one or the other, but as a spectrum. You are either more imperative or more declarative, and it's also highly context sensitive. So one piece of code objectively can be viewed both subjectively as imperative or declarative, depending on the position that you're looking at it from. So we're going to start with what would be traditionally considered the imperative approach. Imperative is often characterized by for loops and if statements. So that's what you'll notice here. What we want to do is go through our list of movie IDs. We want to check to make sure that we have a valid movie ID because we might have some junk data in there. Then we want to look up the movie, get the movie data entry from that movie. And then if that movie is recent, meaning that it was returned since the year 2000, I don't know the relative ages of the audience here, but I'm going to imagine that most of us remember movies before 2000, but let's just call 2000 and later as recent for the purposes of this discussion. And then if it is one of the recent movies, format that movie data entry into the string and push it into an array. And then once we have that full array, and just for the sake of illustration, I'm console logging it out here. Okay, so that is our imperative approach. You see for loops, you see if statements. That is the kind of application code that many people write. Whether you use JavaScript or not, most people tend to default to writing that way. Functional programmers look at that and sometimes kind of cringe and say, ugh, there's a lot of imperativeness going on there. And we don't just say imperativeness because we don't like the code style. Because quite honestly, I actually think that for loops and if statements are not evil. I think they have their place in our programming. But the real reason why we're frustrated as a functional programmer with those things, and many of you I think will resonate, is that we look at those things and we say, oh, well, what that's accomplishing could have these little corners that I'm not really sure. Like I have to really trace through and make sure that there's no gotchas in the code because I don't have the assumptions and the assertions that these mathematical constructs from functional programming give us. So that's the main reason why we might want to elevate this code. It is ugly, but I think we can point out that, again, in the context of JavaScript, this is just about as performant as you can get for processing through the list in this particular case. It's at least in the context of a finite list. that is already present of our movie IDs. This is just about the fastest way you can do that. Now, if we had an infinite stream of data, different story, and we'll talk about that later. But if we wanted to process everything eagerly, all right up front, this is kind of the lowest cost, the nearest to zero cost that we could probably do that. That's good that it has a good performance profile, but again, because it doesn't really use the abstractions that we know to have mathematical properties available to them, sometimes we might say this is a little less than ideal. So let's move into some of our patterns. We're going to start by talking about composition. Now, in programming and actually in the whole world, composition can be, it's one of those words can be used in like a million different ways. And even in programming, be used in means lots of different things. As it relates to this talk, we mean expressing and managing the flow of data through the program. That's what we mean by composition. And we want to express it and also to be able to operate on that expression, meaning to take one composition, one data flow, and augment it. Say, now that it comes here, I want it to also go here, right? So adding on to the end of it. That's what we mean by expressing and managing the flow of data. We're going to talk first about a technique for composition, which again in JavaScript comes through the way of methods on the array values. So arrays, lists, for others from other programming languages. Arrays expose these things like map, reduce, filter, which we'll see here. And what we're saying is that by chaining those arrays together, you are creating a composition. It's a form of composition called method composition. So we could express the same imperative code from before in this style using those filters and map functions. Now notice the alternation here. That's going to be actually really important. We have a dot filter, which is making a decision on is it a valid movie. And then once we've decided that it's a valid movie, we've reduced our list down to a smaller context of only the valid movie IDs. And then we map those valid movie IDs into the movie entries through lookup movie. And then we make another set of decisions, taking those movie entries and eliminating anything that's not one of the recent movies. So we further restrict our list of movie entries down. And then we do one final mapping over the remaining movie entries to create an array of strings. So this style is often referred to as the more declarative style. And you see map, filter, we'll see reduce later. These are kind of the gateway drugs that most people get into functional programming. They see some code using a map or a filter. Actually, many people in JavaScript get into functional by using for each, which is very much not of the functional persuasion, because it is purely side effecting. You don't get values back from the for each method. But people said, they kind of took the drug of, I want to do functional programming. And the first thing they saw was, let me change my for loop into a for each call. But for each aside, we see map, filter, and reduce. Those kind of the typical way that people get into this FP style. Unfortunately, in JavaScript and in many other languages, even though this has an attractiveness in terms of its declarative style, it's pretty straightforward to kind of read the steps in order top to bottom, there are some inefficiencies. And I want to call out two specifically. One inefficiency is that each of those methods, the filter, the map, the filter, the map, each one of those methods has to do an end traversal over the entire list. Now, in our example, our list is super short, so it doesn't really matter. And in fact, maybe the JavaScript engine is even doing loop unrolling or some other kind of optimization. But if the list were long enough, this could be a problem that we are, and if we have lots of steps, it gets even more, right? So you might say, well, it's all still O of n. It's not, algorithmically a more complex process, but for n is going to be slower than n, right? So we're going through this list, in this case, 4 times. That's one inefficiency that we have traded off. We started with the imperative version, we went to an abstraction, but now we've traded off efficiency. And that's kind of this very common trade-off. You go for more declarative code, you often trade off performance. We're going to attempt to try to slay that performance dragon and get back to something that's declarative, but with nearly zero cost. That's the goal of the talk here. The second inefficiency that I want to point out, it's less obvious here, but the second inefficiency is that the filter method, the very first filter method, when it's called, it does not know what you're going to do with that value. So it doesn't return it in any kind of intermediate state. It just returns another full array. These are, in the functional sense, pure utilities, meaning that they don't operate on the same list. They return new lists each time. So we actually have 3 intermediary arrays, one for each of the first 3 steps. And then we get our final 4th list back that we end up console logging on the last line there. So we have both. We are doing end traversal with each step and creating intermediary arrays, intermediate lists with each step. I don't have a ton of experience with a lot of other programming languages, but I am aware that there are quite a few programming languages where if you express a style like this, whether it's method composition or not, you end up with similar performance pitfalls. Hopefully, some of you are going to recognize that in your particular language stack and say, oh, yeah, I've seen that before. I've seen those slowdowns before. Or maybe you haven't noticed, but now you will go back and try to take a look more at your code. So that is kind of our succinct problem statement. We want declarative style, but we'd like to do so with as little of that performance cost as we have to. Let's talk about another form of composition. If we had method composition before, let's talk about function composition. And this is going to be a set of techniques that we build upon to get closer to the solution that we're looking for. Composition of functions means when one function executes, it takes an input, it produces an output. That is the functional programming definition of a function, is that it's a unit of code that we pass something in, alternatively pass something in, but we always get something back out. It's not producing side effects. It's a pure utility. It's just operating on what's passed in and giving something back out. That's a function in the functional programming world, a pure function. And we can compose those pure functions by saying, I'm going to call one function and then immediately take the value of that and pass that as the input to the next. So let's see a couple of examples. First, let's look at a couple of utilities that we'll use on the further examples. We see a compose and a flow utility that I've listed out here, and I've reduced the style of the coding here using arrow functions and things. Some of you that are familiar with that notation, that'll look very familiar. Some of you may not like that. Mostly it was just to save space on the slides. But it is to express that what compose and flow are higher order function utilities, meaning they take in one or more functions as input and return a new function that operates over those inputs. So in this case, we're taking in a list of functions, not technically a list. We're passing in as individual arguments, but that ... is gathering them into a list. So in spirit, we're taking in a list of functions, and then we're iterating over that list of functions and taking each function call's output and putting it into the next input call, and then returning the final result. So those utilities are pretty straightforward. Almost every language that has anything concept of functional programming will have some utility. They're in almost every functional programming library. The only difference here between compose and flow is really the order that they operate on the list of functions. Compose comes from the right, so it starts from the end of the list and moves leftward, if you will. And flow starts at the beginning of the list and moves rightward, if you will. So we could call these compose right and compose left. That's another name that they often go by. All right, so here's a couple of examples. On the first line, you'll see a manual composition where I'm calling lookup movie with some input, 699 being the ID to this movie, How to Train Your Dragon. And then when I get that result back, I don't store it intermediary in any variable. I don't pass it through any other expressions. It's just immediately the input into the format movie function, which is then what gives us that string. So we see here a manual composition where one function call becomes the input to the next function call. Not very declarative, but certainly gets the job done. Anytime you see 2 or 3 or 10 of those steps chained together, functions inside of the argument list of other functions, you start to wonder, could I do a composition, a function composition here? And we see both of those utilities, the helpers from the previous slide, being illustrated. Compose is going to go from right to left. So it's going to first do lookup movie and then format movie. And then flow is going to do the same thing, but in the opposite order. So it's going to do lookup movie and then format movie. Now, you might wonder, why do we need both of these utilities? I'm not going to give you a full and complete answer to that, but I'll just give you kind of an intuition here. You notice that the compose utility, even though it's a little weird to go from the last to the first, notice that the functions are listed in the same order as they appear in the code when we drew traditional infix function calling style, as you see on the first line. So there's a value in in converting our code, if we don't want to have to swap around the order, especially if it's a long list of functions, being able to use the compose utility, it kind of stays in source order. Flow has an advantage that it goes in logical progression from left to right. We generally read programming languages from left to right, so there's an advantage there. You'll find in your programming, you'll use one or the other, and not interchangeably, but you'll use one or the other in various different situations. I probably more use the compose than the flow, I think, because functional programming tends to lend itself to currying, and so you end up with a function last kind of approach. But I use flow plenty, and people who are converting from imperative code use flow quite a bit. All right, so that's working on a single function call where we had two mappers. But what happens, because we know our data flow, our composition is actually a bit more complex, we need the recent movie in there. And in fact, we also need the valid movie. But if we just insert recent movie into the middle of our composition, it all breaks. And this is a big oops. And the problem is that we cannot do a traditional function composition with things that are not mapper functions. The mapper functions that we saw before when we were composing them, that's pretty straightforward, and it's typically referred to as fusion. We can't do fusion. We can't do standard function composition because the signatures are different. In the format movie and the lookup movie, you take a single input and you get back a new piece of data. But the filter function is different. It takes in a piece of data, but it returns a true or false, and it discards essentially the data context. So it's not well suited for this type of composition. So our whole approach to wanting to do function composition as our solution kind of breaks down. So we go back, and this is back to the imperative style, but you'll note that if I just manually list out the things that I want to do in order, I list out the if statements and the lookup movie call and all of that in order as we did back in our imperative example, you'll note that I am indeed able to express a single function with no performance downside that I can pass into the map call, as you see there down towards the bottom. That single show movie function, we're doing one traversal over the list and one set of operations against it. This is effectively a zero cost abstraction for our composition. But it's not an abstraction because we had to manually write it, and that's what sucks. Now, by the way, we need that little filter boolean there because our mapper is not reducing the list when it skips over things, so we end up with a bunch of undefineds in there that we have to skip over. Okay. So we hopefully have a pretty good sense of the problem set. The problem being that we're doing an eager iteration over a list of values. We need to do multi-step, and it's kind of a multifaceted set of steps. There's some conditionals, there's some transformations. We'd like to compose all that together to get as close to zero cost abstraction in the composition as we can, but we're not really seeing that just from straight function composition, and that's where we're going to elevate to a couple of other solutions. The first solution that we're going to look at, we're going to kind of take a sidestep. It's not really going back, but it's a little bit of a detour or a sidestep into yet another performance issue that we didn't address, which we hinted at, was the idea that if we were working on an eager list, no problem. But what if it was an infinitely long list? What if it was a stream of data that was coming in? Well, our eager approach of taking the entire value set and putting it into an array, and especially recreating the array for each step and going over the entire list, that all completely breaks down. There's no way that will work if we're dealing with infinite or indeterminate length, or really just effectively infinite. Even if it's 100 million, you're not going to want to have 100 million items in an array and redeclare that array over and over. You're just going to create way too much garbage collection pressure in the JavaScript system, other out of memory issues in other languages. So that approach won't work. Thankfully, there are lazy iteration mechanisms that are available in most languages. And in JavaScript, it's referred to as generators. Generators are in other languages like Python as well. So some of you have probably seen these before. Generators kind of get a bad rap in JavaScript. I think there hasn't been a lot of very good motivation done for why they're great. They're actually probably my favorite feature in the entire language, or at least certainly my top 2 or 3. Certainly, I think they're the most powerful of all the metaprogramming techniques that's ever been added to JavaScript. So if you work in JavaScript and you haven't really had a full immersion into what generators are. I hope that this kind of whets your taste for that and that you dig into it more, because I use them all the time. I think they're very powerful and useful. But we're going to use them in one particular way, which is to create lazy iterators over our lists so that we could handle something like an infinite list, a stream of data, etc. So I'm going to define two utilities, one for filter and one for map, as you might expect. That it should be pretty straightforward what's happening here. We're going to consume an iterable value by value. And in the case of the filter, we're going to do an if statement. We're going to call that predicate fn function there. And if it returns true, then we're going to yield that value out through the generator. So we're going to produce that value out. And if not, we're just going to skip it. So it has the effect of discarding the value because it didn't pass the predicate. With the mapper function, we're also going through our iterator one value at a time. And we are calling the mapper function, the fn down there, and yielding out the value that produced. What you need to note is that generators do not automatically run to completion. You have to tell them to run to completion. By default, they're going to run a single iteration and then stop and say, here's your value, do with that what you will. And then you can tell the generator, hey, give me another value. Hey, give me another value. So it's a pull rather than a push mechanism. That's what's happening here. So by default, even though these for loops look like they are eager, because there is a yield inside of them, they automatically become lazy instead of eager. And then the interface on top of the generator is what's going to do that controlling. We're not going to interact with that interface too much, but we will see a very small observation of it on the next slide. Here we are expressing the same data composition flow from before, where it kind of goes back to that more declarative, almost method chaining style. We're using a function composition with flow here, and we're calling these individual filter and map calls. Those are each returning their own generator. So in other words, we are composing 4 generators together. And that's a little bit of an interesting thing because it's actually a higher order generator. But we're composing those generators together because one generator takes an iterable from another, and generators are iterables. So we're just saying the generator comes out of one and goes into the other, which is just straight up normal function composition. That flow utility is the same flow utility we saw before, works with any value. So in this case, it just happens to be working that we're passing along our iterator context. Our values will get yielded through those iterators. It's a little bit awkward how we interact with the iterator. Like the DX of the generator is because it's a lower level metaprogramming technique. You notice here that I have to wrap 699 in an array because we're expecting an iterable as the value input, and arrays are iterables, but the number 699 is not. So we need an iterable for it to first consume. And then we have, when we call show movie, it doesn't actually do anything yet. We have to tell it, give me the first result back, do the first processing through the flow. And that's when we call .next on it. So this is a little bit awkward to work with, which means that we could actually create some helpers, and we will on the next slide. But one thing to note, very important here, is that all of these generators, we got 4 generators, they are all running concurrently. And they are in a paused state after they've done each of their steps. So they are staying resident in memory and they're maintaining their own data. They're not running fully eagerly through the list and then returning a whole list. They're just running against one value and then returning that and then pausing themselves. That's what's happening with the yield, is that it's sending out a value and then pausing itself. So we don't have 4 n traversals over our list. We've gotten rid of that. And we're also not creating any intermediate lists here. So we've all automatically, we fixed our 2 main pain points here. Just by going to this particular abstraction, we fixed those pain points. We have other pain points we'll deal with, but we fixed those pain points. And that's the key beneficial observation about the generators. Just by moving to this lazy concept, we can still use it very eagerly like we are here, but just by expressing it in this lazy mechanism, the power of the generators kind of eliminates all of the performance problems, or most of the performance problems that we talked about with the array method composition from before. So this is good. Let's define ourselves a couple of helpers to work with these generators a little better. So first of all, I'm going to have a gather function that can take a list of values and produce an actual array. So it's just that ... operator in function form. It'd be nice if JavaScript had operators as functions, but we don't have that. So then we have a take one, which is going to literally just call the .next on an iterator and then pull out its value from the iterator result, return that. And then take all consumes the entire iterator to its end and puts it into an array. Pretty straightforward helpers. We'll use a couple of those on the next slide. Here we're actually constructing the same function, but now it's a little bit easier to use. You notice that we've inserted a step of gathering as the first step in our composition. And then at the end, we have the take one. So we, in this case, we know we're just going to pass in a single ID for show movie, and it gives us back that single string as the result. So now it's a nicer function for us to use without worrying about the underlying concepts of generators in that interface. We can then lift that to the context of the entire list. Here's back to our kind of original example now where we're going across the entire list of movie IDs. It's a straightforward process to kind of lift that concept because we can do a flow control. We can do a flow composition over those lists. And at the end, instead of using take one, I'm going to do take all, which is I'm going to consume the entire iterator context I've been passed and put all of that into an array. So that's the key difference between the two. And also, we didn't need to pass in the gather step this time because we're going to pass in, as you see there, the flow function returns us a composed function. And then on the very next line, we just call that composed function with our movie IDs list. Again, keep in mind that the array is automatically an iterable, so it can be consumed by our iterators or generators here. Okay. So this really has actually moved the ball forward, and we didn't have to do hardly anything. We just had two very small little helpers that we defined. We had to change our context, our mental context, to working in a lazy form, but we're doing an eager iteration with a lazy mechanism, and it works great. And it has, again, gotten pretty close to a zero cost. Not fully, but pretty close to a zero cost. Now, you might be wondering, well, if these are such great little helpers, why aren't they just built into the language? And people have been asking for that and for other helpers like that for quite a while. Besides the map and the filter one, there was about a dozen others that we've been kind of begging JavaScript to finally add. And great news is that they did add those to the iterator interface. That landed, I think, last year. So it's pretty standard across most modern JavaScript environments now. So we have these built-in iterator helpers. We don't need to define our own little map or filter function. Now we can just use them directly on our iterators. And I want to point out, I've used a couple of terms that sound interchangeable, but just to keep the terminology for JavaScript straightforward. In JavaScript, an iterator is an interface that produces values. An iterable is an interface over the collection of values. So it's like the data structure itself. Whereas an iterator is the thing that is going to process and potentially produce value. So those sound like almost the same, but they are distinct concepts here. So an array, for example, is an iterable, but a generator is an iterator. These helpers help us work with generators then, because these are iterator helpers rather than iterable helpers. So just keep that straight. We still have all of our normal eager iterations over array lists, the iterable helpers, if you will, like map and filter and reduce. We still have all of those, but we now have lazy versions of all those on the iterator interface through generators. By the way, if you want to read up on that proposal, it's already been added to the spec, but if you want to read all the discussion of that and go through all the lists, the issues list and see how they came to these designs, that repo is still actually really valuable information to learn about. But here is our running example expressed with the built-in iterator helpers. The only difference that you see now is that we've switched back to a method style of composition. And you'll see on the first line, we're doing iterator.from, which is going to turn our iterable, the array movie IDs, into an iterator, a function generator. And then on the very last line, we've got the toArray, which is going to go in the opposite direction. The toArray function takes us from an iterator and potentially lazy infinite iterator down to a finite, fully consumed array list. So we go into the iterator, we do our composition, and then we step out of the iterator back to an array. Even though those method calls look the same as the array method calls, they don't have any of the downsides of array method composition, because under the covers, these methods are doing that same context sharing through the generator interface that I showed a couple of slides back. So we've gotten rid of all the multiple end traversals. We've gotten rid of the intermediary arrays. The one downside that we still have, which is unfortunate, is that the generator interface is a bit complex because it's such a powerful metaprogramming tool. And we have one instance of the generator for each of our steps in our composition. And many times our steps of our composition are not just 3 or 4, but they can be like 10, 12, 20 steps for modern complex apps. So all those generator instances are hanging around in memory until the entire iteration is complete. And there is a bit of inefficiency to yield a value out and consume it through the generator interface. So it's not zero cost. It is better than what we had before. It is certainly an improvement, but it is not zero cost. So it doesn't fully represent the solution that we were hoping for. The good pro, of course, is that this mechanism is extendable to the lazy infinite list scenario where our other solution was not at all. This fully works the same whether you're working on a finite small list or an infinitely sized lazy list. Okay, but I've been hinting that there might be something that's going to get us much, much closer, if not exactly to a zero cost composition abstraction. So let's dive into that. We're going to use this other technique, which I'm going to forewarn you, if you haven't looked at this before, it might be a little bit mind-bending. Certainly took me a while to dig into this code and take it apart and rewrite it myself. But these utilities are actually not that complex, and they're small enough and straightforward enough that I'm going to be able to fit them all on one slide. So there's not some hidden magical library that's a framework that's going on. It is straightforward enough to go on one slide, but you do have to kind of get your brain wrapped around this mathematical trick of transducing. So before I even show the code, what is a transducer? It is a higher order reducer. You know, a higher order function is one that takes functions as input and produces new functions. Well, a higher order reducer is a function that takes reducers as input and produces another reducer. And you probably, hopefully, remember what a reducer is. A reducer is just a function that takes an accumulator and a value and combines them, right? So we're just talking about a higher order version of those. Transducers are higher order reducers. And the trick that we're going to get here is if we can represent all of our steps of composition as these transformed reducers, as these transducers, then we'll be able to compose them all together in one single big chunk. So it'll be a one shot that will do all of our steps, kind of like our imperative show movie function that we had illustrated before. So we're doing a mathematical transformation on these things instead of having to manually and imperatively write that function. We'll check, make sure. All right. So here are the utilities that I was referring to. This is basically the heart and soul of what transducing is. Represented, of course, in JavaScript, but small enough that you can actually see it formatted out on just this one slide. So we see mapT is a utility that takes in a mapper function like the format movie that we talked about, or the lookup movie, those mapper functions, as its first input. These are just manually curried things. So if you're not familiar with that notation of the arrow functions, I just put each step on one line so that it's clear, because I get lost in all the arrows when they're all on one line. So that's why I've broken them out onto multiple lines here. But the first step is we're going to pass in a mapper function, and we're going to get back a function that expects what I'm calling a combiner function here. That's just a fancy way of saying it expects a reducer. So when I call mapT and I pass in something like, for example, format movie, I'm going to get back this function that expects combiner function. That thing is a higher order reducer, aka a transducer. So mapT is not a transducer. It is a function that will produce a transducer. You give it a map function, you get a transducer back. Same way with filterT. We pass in our predicate function, we get back a transducer that's expecting a combiner function. Higher order reducers here, once they get their reducer, once they get their combiner function, they produce a new reducer. And you'll see there that the last line of each of those functions is a standard reducer. It takes an accumulator and a value. And in this case, for mapping, it maps the value with the mapper function. And then it combines that with the list using the reducer that's been passed in the combiner function. So I don't do like list.push here. I'm just doing list and mapper of fn of v and telling the combiner function, you figure out how to put those two values together. So there's a little bit of an abstraction there. Same thing with filter t. I call the predicate function. There's a ternary there. If that passes, I pass the value and the list into combiner function that I've been given. Otherwise, I just return the existing list because I didn't need to do anything with that value. So it discards it. Transduce L, meaning transduce for lists, is a higher order function, of course. It takes in a function. In this case, that fn there is a transducer. So it takes in a transducer and it calls that transducer, you'll notice there in the next to last line, with concat L. Concat L, you'll see on the very last line, is nothing more than a list concatenator. It just takes a value and concatenates it on, appends it to the end of a list. So when I call fn with concat L is the combiner function of our composed transducer. And so that's the ultimate thing that comes in and says, hey, when we get these two things and we need to stick them together, the way we stick them together is just shove values onto the end of a list. And then I take the result of that transducer call, the fn with concat L, that just produces reducers, right? A higher order reducer, a transducer, it produces reducers. Well, I get a plain old simple reducer that, by the way, has all of our steps already composed into it. And then I just do a single reduce call. So that reduce call in the next to last line is the magic. We're going to go once through our list, and we're going to do all of the work in one function call that is our one big mathematically composed reducer that we got back from our composed transducers. Lots of words that I just said. I'm going to encourage you. You'll probably want to go back and reread some of this information, go re-listen to this recording. But let me just show you how that looks in our code, because it's going to be, I hope, a lot more graceful than explaining how transducing works. So you'll notice, first of all, in the innermost part, we're using compose, kind of like we were using flow before. I'll explain why we switched. But we're just doing a composition of these things. Now, remember, filter T is going to give us back what? It's going to give us back a transducer. So we're basically composing 4 transducers together. And you remember that a transducer is a higher order reducer. It's expecting a reducer as input. So at some point, we're going to need to pass in a reducer into that composition. And then those reducers are just going to produce another reducer, which produces another reducer, which produces another reducer. And we get back one giant reducer. That is our composition. And that thing is what we're passing into transduce L, that transducer that we're passing in to transduce L. And transduce list, transduce L, you remember it takes a transducer and it passes in under the covers the concat L utility. Because we can do transducing for all kinds of values, not just for lists, but here we're doing it with lists. So I'm just kind of simplifying. We're transducing with a list, so it's kind of hardwired to use the list concatenation to do its work. And transduce L produces one function who's expecting a list of IDs, which we pass in as movie IDs, and we get back our finished list. So what we have now done is taken our existing application code, the valid movie, lookup movie, recent movie, format movie. We have mathematically transformed those into reducers, into higher order reducers called transducers, composed all of those transducers into one big transducer, taken that transducer and made a reducer from it with the list concat, the concat L utility, and then done a single reduction over the movie IDs list to get back our newly reduced and transformed list. We've done all of that with one single n iteration through the list, so we don't have multiple n iterations. And we've done all that with no intermediary arrays because it's just one giant function that's operating on each value. So we now have gotten back to the same kind of zero cost promise that our previous attempt with the lazy generators gave us, but we do not have anything sitting around in memory with these complex interfaces of generators. You saw the entirety of transducing on the previous slide. There's nothing else to it. It's just those function calls. And by the way, if I were to go back to that slide for just a moment, one thing I forgot to point out, you'll notice that each of our two reducers, look at the list that says combiner function, list mapper function, and then the one that says predicate FN with the ternary. Those two lines of code, those are what we call tail calls, meaning that the function call stack is at the end of the function call. And in JavaScript engines that have implemented tail call removal, like for example, Safari in strict mode has this, then it will literally at the compiler level optimize away all those function calls, and it'll just be one single set of code with no function call overhead at all, literal zero overhead abstraction. I wish all the JavaScript engines had implemented the proper tail calls, but we at least got one of them. We know that Safari did it with the strict mode. And I'm hoping someday, maybe if more of us functional programmers keep begging for it, all the other engines will catch up. But what we've got now with our transducing is kind of our magical unicorn solution. We have a declarative approach that uses functional programming techniques, and it removes, because of the way that the transformation works, it removes the inefficiencies that are inherent to this type of composition. So we get almost a perfect zero cost abstraction with only having to pay a couple of function calls in the list instead of having to pay for n traversals or all those intermediary arrays and garbage collection and all of that. So that's a really great outcome. It did take us having to wrap our brains around a slightly more complex technique, this transducing, but hopefully it's not too intimidating and you can dig in a little bit more. I have one last thing I'm going to finish with, one last kind of bonus that I'm going to finish with, which is that we've been talking this entire time about synchronous composition and synchronous data processing. But what about asynchronous processing? I said that we kind of faked it with the lookup movie being just operating synchronously over an existing in-memory data. That's not how our real applications are going to work. It's going to be making a fetch call to an API or whatever, reading something from the ElectricSQL database that James talked about, something. It's going to do something asynchronous. And we still want to be able to have all the guarantees, all the nice declarative abstraction, and none of the performance overhead. How do we do that? Because none of what we've shown so far seems to lend itself to asynchronous programming. You might guess that the reason why I'm talking about this is because there is a solution where we can extend all of these concepts, even transducing and composition, into the asynchronous space. We can lift everything up in JavaScript terms, lift everything into promises. That is a bit more complex than what we're going to go through in this talk. There are some gotchas that we have to worry about when we're lifting everything into the promise space. And it's not the kind of thing that you want to inline the code yourself. It is the kind of thing that somebody needs to implement in a really nice, clean, simple library. And hopefully you're going to enjoy the fact that I created such a library. And so I'll show you that library. It's called FASY, F-A-S-Y. It stands for functional asynchrony. So let's take a look at how we would use the FASY library to do our same example with transducing. So we get the zero cost abstraction, but we can now work with it over asynchronous methods as well. You notice at the top, I'm importing the serial interface for composition and the transducers interface to be able to work with this. There are other things, of course. FASY supports both serial and concurrent compositions and iterations. So you can go and take a look at all the different things that you might want to import. But here I'm just using a small portion of the library. We're doing a straight up normal compose. That's what fas.compose is. And then we have our 4 transducers represented by the fat.filter.map.filter.maps. So we're doing our same composition. I'm using the into method, which is a slightly different way. It's kind of like the transduce-l, but it's a little bit more generic because it's saying into what. And in this case, we're going into an empty array as opposed to into a string. If we passed it an empty string, it literally would have done the exact same thing, but it would have string concatenated rather than putting separate entries into an array. So that shows you that transducing is more general than just list processing. But the real key thing here is that if valid movie or lookup movie or any of these steps are asynchronous, this code just magically keeps working because it's all been lifted in the promise space. And we see that final await call there, awaiting the result of the into method. When that promise resolves, all of those steps will have finished. And so we don't have to worry about any of those problems. We couldn't do any of the asynchronous processing with any of our previous examples, list methods or the generators. They don't automatically deal with the asynchrony, but here this FACY library does handle that complexity for you. And it provides you the composition and transducing that we talked about. So it's kind of the best of all possible worlds. So the last thing I'll point out is that even though this is designed to work for asynchronous operations, you could literally use FACY for purely synchronous operations as well. Because under the covers, it's just lifting everything, so it won't matter. Slight overhead of dealing with promises, but it'll have the exact same capability. So you could just standardize on using FACY for both synchronous and asynchronous transducing and composition. Mix and match as your application sees fit. I use FACY on quite a few of my projects. It's been around for a number of years. I have no idea how many people have also found it because I don't market a lot of my open source projects. But hopefully those of you listening here today are intrigued a bit and want to go check that out. So that's what I've got for you. All of the code in those slides, because all that was very heavy code, that's all up on a gist, and you can get that from the QR code there. And then my slides today, the QR code on the right will provide you a link to those slides. Thank you all very much for listening.
Thank you very much, Kyle. That was very nice explained. Like, you know, like this is, here you have the loops, here you don't have the loops.
Right.
And really
well,
like
you
going
have the
through
loops,
it.
but they're buried below, right? They're
Exactly.
handled by somebody else. You don't have to write them. Yeah.
Exactly. Very nice. Very nice. Question from the chat. As someone who doesn't do more JS than I absolutely have to in my job, what are some of your favorite features which might make me a bit more keen on it?
I already mentioned one of those, which is that I love generators and being able to handle the complexity of that. The main thing that I like about JavaScript is one of the main things that most people dislike about JavaScript, so I'll be slightly controversial here. I actually think that JavaScript's type coercion capabilities are a very key core strength of the language. The vast majority of the modern development community says JavaScript types suck, they're poorly designed, they're buggy, they're horrible, and they've even invented whole new languages like TypeScript to slap on top just so that we can never have to worry about any of that stuff again. The one point I'll make about that is that you cannot get away from the fact that your code is running in a JavaScript system. And even if you write TypeScript, you're going to have to deal in certain corner cases anyway with JavaScript's coercion capabilities. So I would actually recommend you should really lean into that rather than trying to hide it away as much as possible. And so that's one of my favorite things because I don't worry about those problems because I learned JavaScript coercion. And I don't need things like TypeScript to help me be type aware. I've just learned the rules of how JavaScript's mechanism works. So I know that's a very controversial take that I'm just about the only one who will say so, but I really do think that JavaScript's coercion system is a strength. And then I guess I'll just pull out a slightly more modern feature that came in. We added optional chaining, which again, if you're a functional programmer, you're used to working with things, maybe used to working with things like monads. It's not actually the option or the maybe monad, but it's very similar in approach, and it still kind of marries to the imperative style of dot operator data access, and it just uses a nullable check on that. I'm actually a big fan of that because there's a whole lot of really imperative if checking guards that you have to do to get around that problem in JavaScript, and they landed that one operator, and most of that code just got deleted. So even without having to go all the way up to monads, we got a big capability just by that one tiny operator. So off the top of my head, those are the three that I would say are very attractive about JavaScript. I don't know that they're going to pull anybody from some other language to JavaScript, but if you're in JavaScript or JavaScript curious, I recommend at least doing a little bit of study in that. By the way, in coercion, I read a whole book about that. It's up on my GitHub. So if you want to read more about my thoughts on that stuff, I've written quite a bit about it.
Thanks. Next question. Is RxJS a similar library?
Ooh, no, it's not a similar library. That's kind of like asking, is this Titanic the same thing as my Apple in my hand? They're very different things, and Rx is very much bigger and more complex and does a whole lot of things. You probably could represent at least some parts of the examples from today using Rx, but you absolutely would not get to essentially a zero cost abstraction the way that I tried to show. So you pay the penalty of staying in their abstraction layer, you getting all this extra power, but if you don't need it, you really should not be using something like Rx. But just for the audience's sake, Rx is it's the observables pattern implemented in a bunch of different languages, including the RxJS, the JS port of it. So it's these complex concepts, but it really boils down to the ability to have streams of data that you subscribe to or that you push data down. So you get both a push and a pull interface over streams of data. That's kind of one of the main ways that people do streams-based programming or kind of observable-based programming in JavaScript. There have been some attempts to try to add something like that into the DOM API standard, and therefore it would kind of come for free in JavaScript. I don't know where those stand, but Rx itself is a pretty big and complex library. It's a lot of learning. And everything that I showed you here today, with the small exception of Facey, everything I showed you here today fits on a slide. So I prefer small mental context rather than take on the giant mountain to do one tiny task.
Yeah. Next question. How does failure in the async stream be handled on any one of the pipe function?
So if we're talking about Facey, the way failure happens at any point is that it's lifted to a promise rejection. So you handle that, you receive a promise rejection in the same way that you'd handle any other asynchronous rejection. If we're talking about in the transducers or the other function, you're going to get a synchronous exception in your call stack, and you are unfortunately going to get a really complex call stack with all those intermediary function calls happening. That's one of the reasons why I was referring to the idea that having the zero cost abstraction from the tail call elimination is so beneficial, because in a language that supports that, or I mean in an engine that supports the tail call elimination, you would actually theoretically have all of those intermediary functions not even show up in your call stack, because the JavaScript engine treated them as if they didn't happen, because it kind of did all the inlining and stuff. So that's the reason why we want zero cost function calls, and the zero cost abstraction is actually not only for the performance, but for the debuggability. It is more complicated to, well, just it's more tedious to go through these long call stacks and filter out all the stuff that's just those intermediary function steps. Other languages besides JavaScript have strengths there in that their compilers do a lot of that removal of those layers, and JavaScript doesn't, unfortunately. But that's one of the reasons why I highlighted the tail call positioning of transducers, is that they at least make themselves friendly to that. If we could get more engines supporting it, it would be a much improved debugging story. And then the same thing with generators. Those act, even though they look asynchronous, they act synchronous. So you would just, even inside of the generators abstraction, you would end up with a synchronous exception reported in your, with a call stack or something like that. Modern JavaScript environments like the browsers and Node and stuff support asynchronous call stacks. So even if it was across asynchronous steps, you would still get a full call stack there. So that's the difference between Phasey. You would get it as a promise rejection. Everybody else, you're just going to get a big, tall stack exception list in your console.
Okay. Thank you very much again, Kyle. I have one last question. How come you get into this? I mean, if you work with JavaScript, the typical JavaScript developer I know, they don't at all view this or try to get into this type of optimizations, etc. or don't at all, like these function compositions you have done?
Yeah. So my answer is that my ultimate goal is to write the best code,
Mm?
not to write the most popular code. I've never been driven by what is popular or what is marketable. I've
Mm?
always been driven by what is the most correct. And I think everyone in this audience, since you're a functional programming community, you'll agree with the sentiment that, at least for me, the main attractor to functional programming is that I don't like writing code that I don't understand or that I'm not sure what it will do. I
Mm.
do not like the cycle of write some code and then cross my fingers when I run a test case to see if it passes. I want to write code that I understood, that I intended, and that I am certain will produce a certain an outcome. That doesn't mean I'm going to write bug-free code. I'm going to write bugs, but I don't want my bugs to be around things that I very much could have had understanding over. In other words, I want to reduce the surface area of where my bugs can happen. And ideally, I want my bugs to be business logic bugs rather than programming logic bugs. And that's
Mm.
the attraction to me of functional abstractions. It's one of the reasons why I'm recommending that modern JavaScript do away with all the frameworks and go towards a more monadic approach. And I'm the only one out there saying that, because everybody says, well, if you want to do monads or whatever, go to some other language. I think front-end programming and JavaScript and web app programming would benefit from embracing these ideas. And I went on that path of trying to learn how these things work. It was not an easy path. I don't
Mm.
think there's a lot of great resources there, but I wrote a whole book about embracing functional programming in JavaScript and embracing what JavaScript is, but also bringing in the functional approaches to it, because I believe those two things can be married together. And I tried to leave that as kind of some better breadcrumbs for folks that want to go on the journey. But ultimately, you have to decide that you're not going to wait for some other framework author to solve the problems that keep plaguing your app. And I think that's what most developers are doing, is we're just waiting for the next better silver bullet, the next version of React or the next Vue or the next whatever. It's going to fix all my problems. And it's not. Uh, there is no singular tool that's going to fix those problems. Your knowledge is the only way to fix those problems. And I've dedicated my career to helping kind of voice the need to move in that direction. I chose JavaScript a long time ago, and I haven't needed to move off of JavaScript, although I have interest in other languages as well. But I don't feel like I need to leave JavaScript behind because JavaScript is completely incapable. I can advocate for doing things in JavaScript a different way. And that's one of its strengths, is that it is so malleable. You can do a lot of different styles. And I think among the infinite ways that you can express a program, there is a subset that's a lot better than the rest.
Mm.
And that's what I've been trying to attract more people to. You know, the final thing I'll say about JavaScript is it's not the end all be all language. I write it every day because it's a very powerful tool. It's malleable. It allows me to do a lot of what I want to do, but it's not everything. And I've made a lot of complaints about JavaScript over the years. I've said my piece in social media about what I wish they would do differently. I've advocated for changes. They've never listened to anything that I said. I'm just some outsider who has opinions, and I don't get to influence JavaScript in that way, except through, the knowledge transfer with my books or things like that. But um, I decided a couple of years ago I did not want to spend whatever's left of my career complaining about JavaScript. I instead wanted to be part of building something that I thought could be better and could solve things, not to replace JavaScript, but to augment our options. And so I started designing a new programming language, a functional programming language. And I have a full design for that. I'm working on the tooling to spin that up and bring that out. If any of you are interested, it's called FOI, FOI, and you can find that out on my GitHub. Maybe it's a great language, maybe it's a terrible language, but I'm at least, instead of just sitting around and complaining about what JavaScript isn't, I'm trying to design something that I think is what I wish a language would be.
Thank you very much, Kyle, and thank you very much for your elaboration. Thank you. And again, we'll put out all the links and everything once we're done with the live streaming. We put it out, everything, below the video, so you can find to Kyle's and to James' different libraries and to slideshows and etc. Again, thank you very much, Kyle. And thank you very much, everyone, for this kickstarted first Func Prog Sweden of the year. And see you next time in February. Until then, have a nice time.